Definition of composition of functions. Hello everyone. Today, we are going to explore a fundamental concept in algebra called the composition of functions. To start, let's think about how functions work. In our previous lessons, we've learned that a function takes an input and produces a specific output. However, in many mathematical and real-world scenarios, we encounter situations where the output of one process doesn't just end there, but instead becomes the immediate input for another process. This line is covered by the previous voiceover section, explaining the process of one output becoming another input. In mathematics, this chaining of functions, where one follows another in a sequence, is formally known as the composition of functions. In the upcoming slides, we will move from this general idea to a more conceptual understanding using a factory analogy, and eventually, we will look at the formal mathematical definitions and formulas. Conceptual understanding. Now, to help you visualize this concept of chaining that we mentioned in the previous slide, let's imagine a production line in a factory. Think of the first machine in this line as function f. This machine takes in a raw material, which we can consider our initial input, and processes it into a semi-finished product. Next, we have a second machine, which represents function g. This machine takes that semi-finished product and processes it further to create the final product. It is important to realize that the second machine cannot begin its work until the first machine has completed its task and provided its output. In the same way, function composition in mathematics is a process where the output of the first function serves as the direct input for the second function. This conceptual bridge will make it much easier for us to understand the formal mathematical definition in the next slide. Formal mathematical definition. Now that we have a conceptual understanding of the production line, let us translate that idea into formal mathematical language. First, let us consider two functions, which we will call f and g. To define how these functions interact, suppose we have three distinct sets: set A, set B, and set C. We define function f as a mapping from set A to set B. Following this, we have function g, which is a mapping from set B to set C. The composition of g and f is a new function created by combining these two. We denote this using a small circle symbol as g circle f, which can be read as g circle f, or g composed with f. This resulting function allows us to map elements directly from the starting set A to the final set C. Looking at the mathematical formula, for any element x in set A, the composition g circle f of x is equal to g of f of x. This notation tells us that we first apply function f to x and then apply function g to the resulting value. However, there is a crucial requirement for this process to be valid. For the composition g circle f to be well defined, the range of function f must be a subset of the domain of function g. In simpler terms, this means that every output produced by function f must be a valid input that function g is capable of accepting. If the output of the first function is not compatible with the second, the composition cannot occur. Step-by-step process of composition. Now that we have established the formal definition and the factory analogy, let's break down the actual process of how to evaluate g circle f of x. To do this correctly, we follow a specific logical sequence. First, in step 1, we begin with our initial input value, x, which must be a valid element from the domain of function f. Moving to step 2, we apply the function f to this value x. This operation gives us an intermediate result, which we denote as f of x. In step 3, we reach the core of the composition process. We take the result we just found, f of x, and use it as the new input for function g. Finally, in step 4, we apply the function g to the expression f of x. This gives us our final output, which is written as g of f of x. By following these steps, you ensure that the functions are applied in the correct order. In the next few slides, we will see how this logical flow works in both real-world scenarios and abstract mathematical problems. Real-world example, shopping discounts and taxes. Now that we have discussed the formal definition and the step-by-step process, let us apply these concepts to a real-world scenario to see how function composition works in practice. Imagine you are purchasing a laptop. In this situation, there are two sequential operations applied to the price of the item. First, a discount of $100 is applied. Following that, a sales tax of 10% is calculated based on the already discounted price. Let us break this down into mathematical terms. First, let x represent the original price of the laptop. We can define our first process as function f of x, which represents the discount. Mathematically, this is written as f of x equals x minus 100. Next, we define our second process as function g of x, which represents the sales tax. This is written as g of x equals 1.10x, which is the mathematical way of adding a 10% tax to a value. To determine the final price the customer pays, we must use the composition of g and f. Denoted as g circle f of x, we use this specific order because the discount must occur first, and the tax is then applied to that resulting value. Let us walk through the calculation. First, we apply function f to our original price, which gives us the result of x minus 100. Now, as we learned in the previous slides, the output of the first function becomes the input for the second. Therefore, we use this result as the input for function g, which gives us g of f of x, or g of the quantity x minus 100. Finally, we substitute the expression x minus 100 into the rule for function g. This gives us the final composed function. G circle f of x equals 1.10 times the quantity x minus 100. This example perfectly illustrates the chaining effect we discussed earlier. Now that we have seen how this works with a real-world example, let us move forward to a purely mathematical example to refine your algebraic skills. Mathematical example. Now that we have seen how composition works in a real-world scenario with discounts and taxes, let us apply those same principles to a purely mathematical example to solidify your understanding. Let us consider two functions, f and g, both mapping real numbers to real numbers. Function f is defined as 2x plus 3, and function g is defined as x squared. Our objective is to find the composition of g and f, which is denoted as g circle f of x. Step 1, we begin by writing the formal definition. G circle f of x is equal to g of f of x as we discussed in the previous slides. This notation reminds us that the function closest to x, which is f, must be evaluated first. Step 2, we substitute the actual expression for f of x into the formula. Since we know that f of x equals 2x plus 3, our expression now becomes g of 2x plus 3. Step 3, now we apply the rule for function g. Since the rule for g is to square whatever input it receives, we take our entire input, 2x plus 3, and square it. This gives us the quantity 2x plus 3 squared. Step 4, finally, we expand this algebraic expression. By squaring the binomial, we arrive at the final result, 4x squared plus 12x plus 9. This completes the process of composition. In the next slide, we will examine some common mistakes to avoid, such as performing the operations in the wrong order, to ensure you can handle these problems accurately. Common mistakes to avoid. Now that we have walked through the conceptual and mathematical examples, it is important to address some common pitfalls. Let's look at the most frequent mistakes students make when dealing with function composition. First, let's discuss the order of execution. A very common error is assuming that g circle f of x means you apply function g first and then function f. Please remember, in the notation g circle f of x, the function closest to the variable x, which is the one on the right, is always the one applied first. Think back to our factory analogy. The first machine must finish its job before the second one can begin. Secondly, be careful not to confuse composition with simple multiplication. It is easy to mistake g circle f of x for g times f of x. To be clear, g times f of x simply means you find the value of g of x and multiply it by the value of f of x. However, g circle f of x is a composition, meaning you substitute the entire function f of x into the function g. Lastly, do not ignore the domain. As we mentioned earlier in the formal definition, you must ensure that the output produced by function f is a valid input that function g can actually accept. If the range of the first function does not fit into the domain of the second, the composition is not well defined. Keeping these 3 points in mind will help you avoid the most common errors. Now, let's wrap everything up with the key takeaways. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of the concept. First, remember that function composition is essentially the process of applying one function to the result of another. Think back to our factory production line analogy. It is that chaining effect where one process leads directly into the next. Regarding the notation, it is important to be comfortable with the symbols. When you see g circle f of x, this is mathematically equivalent to writing g of f of x. This notation simply tells us that we are nesting one function inside another. As we discussed when looking at common mistakes, order matters immensely. You must always evaluate the inner function, f, first. The output produced by f then becomes the input for the outer function, g. Just like in our laptop example, you cannot apply the sales tax until after the discount has been subtracted from the price. Finally, always keep in mind the essential condition for a composition to be well defined. The range of the first function must be compatible with the domain of the second function. In simpler terms, the output coming out of the first function must be a valid value that the second function is actually capable of processing. If you keep these 4 points in mind, you will be well prepared to tackle more complex composition problems.